So today we're going to focus on estimating limits graphically, and then tomorrow we're going to talk more about how to do them algebraically, and then when you guys get to your final exam, it's going to be a little combo of that. And frankly, some of the questions you can do in either method, and maybe at that point you'll decide which method you think is easier for you. So we are definitely going to be testing you on estimating limits at a point. But we will not be testing you on estimating limits at infinity. But we are going to discuss it in our lesson, simply because this is kind of the moment where everything comes full circle for you. All our ideas of end behavior, like this is where it's all leading up to. And this is the beginning of calculus. So hopefully after the next 2 days you realize that, you know, calculus won't be too terrible. It's not like it's full of stuff that you've never heard of. That's the good news, okay? So this picture here describes what a limit looks like, estimating a limit at a point. And you have, it looks like a line, but if you guys look carefully, there's actually an open circle here, which we called a hole. So this is a rational function that was graphed that has a hole, a removable discontinuity. Remember I was talking about those back in rationals? So if I try to evaluate this function at this exact value, I would have an error on my calculator because it would say it doesn't exist because there's a hole there. But if you approach it from the left side or the right side and you get really close to it, it does seem to be approaching a specific value, and that's the idea of a limit. So even though you can't directly evaluate the function, you can tell me what the limit is approaching. One way we can do that is a very tedious way of using a table. So we would put our table in ask mode, and we would be figuring out numbers that are approaching that particular number. So like this one, for instance, it says as x approaches 2. This is the limit notation that you're going to be seeing a lot today. Well, guys, this is a line. So if you had to figure out what happens on your line as you approach 2, wouldn't you just plug in x equals 2 like a normal human? Yeah, me too. But they're saying, no, but wait, you could do something else. You could plug in numbers that are really, really close to 2. So like, what about 1.9 and 1.99 and 1.999999999? And then on the other side of 2, what about 2.1, 2.01, 2.001, or even closer? And look what's happening on your table, guys. What y value does it seem to be approaching? -5. I bet when we plug in 2, we get -5. Yep. That's the idea of a limit. Curious, right? Huh. Really mind-blowing on a Wednesday. Like, okay, that's great. So maybe we need to talk about why we'd have to do this, because we're looking at some of these functions going, I don't really know if I'd have to be doing this. Well, let's look at this one. This is a rational function. And if you were to plug in x equals 3, do you see that there would be a problem there? Because you'd end up with a divide by 0, which we know as a discontinuity. But turns out, and we'll talk more about this tomorrow, algebraically, I could do some factoring on that polynomial up in the numerator, and we would see some removable discontinuities cancel out. And that's why we're going to see a hole on the graph. However, let's pretend we're just approaching this from a limit standpoint. Since I can't actually plug in a 3, they're claiming, well, why don't you just plug in numbers really, really close to 3? And I go, okay. So maybe I'd put in the function into my calculator and go to my table again. So numbers that are really close to 3, 2.9, 2.999, 2.99999. And then on the other side of 3 as well. What value do you feel like it's trying to approach here? A 6. That's exactly right. So there happens to be a hole at the ordered pair 3, 6, but the function is approaching the value of 6 on either side of that value. All right, we talked about putting our table in ask mode. That's a very boring process, guys, and I know you're like, she's going to make me do that, isn't she? Yeah, I am. Let's look at these diagrams. These are from your textbook, and this is a good example of limits and what's going on with the different possibilities. So you could have a function where as you approach the value of c, the limit is approaching a value of, they're calling it L for limit. So there, whoopsies. There is some value L, which call it whatever you want, but it's approaching the same y value from either side there. But look at this picture. Do you see the difference? It's still approaching from either side, this value where the hole is located, but right above this, do you see they have this random ordered pair? So this is a discontinuity of a different sort, and we've seen this before where while it is approaching a certain limit, when I actually evaluate this, what is a piecewise function, it doesn't give me the same value. So this is a case where the limit and the function evaluation don't match, and this is a definite discontinuity going on in this graph, okay? So the limit doesn't match the evaluation of the function. We'll talk about what that means later. And then this last picture here is when it's when magic happens, okay? So there's continuity. The value of the limit and the value of the function give you the same value. That means there's no break in it, there's no jump, there's no hole, everything is smooth essentially. So that would be the easiest question I can give you, is something that doesn't have any breaks, jumps, holes, no oscillations. And you could very easily determine what the value of the limit is, or the function itself. So big idea here, guys. The limit is a y value. So if you think about it from the standpoint of end behavior, it's the f of x approaches part of end behavior. Okay, so the limit is what height is it trying to get to. So we have two types of limits that we're going to discuss. You have a one-sided limit versus a two-sided limit. So one-sided limit would be they're just approaching from the left or the right side. And the way that they're going to signify that in your book and in your calc book as well is they'll put a little negative sign or a little positive sign right above in the corner of the number. So if it said like 2 with a little negative sign, they're saying from the left side of 2. So give me some numbers that would sit on the left side of 2. Something really close. 1.99, yeah. 1.9999. Should I bother trying 2.01? 2.001? No, because that's on the wrong side. So if it's a one-sided limit, you're only going to be looking at values on that particular side. The reason we have one-sided limits is because we're going to see in a minute that we are going to have some rational functions where the vertical asymptotes, like one branch goes up to infinity and the other branch goes down to negative infinity. So in that case, if I give you a one-sided limit, you can give me an answer, but if I ask you for what's called a two-sided limit, then we're going to be in trouble. So if it's not a one-sided limit, that means it's a two-sided limit, meaning they won't put any symbol on the c value there. They'll just say like as x approaches 2, and that indicates you're looking at both sides of 2. This is on your notes. Basically, it summarizes what we just said, so moving on. Let's look at the one that's on your notes here. Look at that baby. Anyone remember who that guy is? It is a piecewise function, technically. It's called the greatest integer function, and some of you called it a step function back in the day. Yeah, and it looks like steps, so good job, math, on naming that. The idea is for the greatest integer function, it always rounds down to the previous greatest integer. So like if you plugged in a 1.2 into the greatest integer function, it would round it down to 1. If you plugged in a 2.9, it would round it down to 2. It always rounds down to the previous integer until you get to the next step. So the question they have for you here on your notes, get my pen working. They said, let's estimate some limits. You go, okay. So this first one, where it says, estimate the limit of this function as x approaches 2 with a little negative symbol in the corner. What does that mean? To the left side of 2. So, where's 2? Here's 2. There's a hole there, so I can't really do much there unless I look at the next step. But go to the left side of 2. What y value, what limit are we looking at there? What height? A 1, yeah. So that's what they have right there. And then it says, well, what about if you go to the right side of 2? So on the right side of 2, you hop up here. Well, what height is that at? A 2. So the limit on the right side approaches 2, the limit on the left side approaches 1. So then the question is, well, what about the limit as a whole? So if I make it a two-sided limit, the issue is they approach different values on the left side versus the right side, and that is why the limit does not exist. The limit does not exist. Mean Girls. Watch it. I'm going to... Oriana and I understand.
Oh, well, she made me watch it. I don't...
You still don't appreciate it?
I mean, I'm supposed to. I mean, high school sucks, but...
Right. All right, here we go. Let's take a look at, this is not on your notes, but it might be a good one for us to look at. So look at this fun little rational function. We notice that there is a discontinuity at x equals 4. So it's not like I can evaluate like by plugging in an x equals 4 because we'll have a divide by 0. But if you look at the left side and the right side of 4, our function's branches are going up, up, up on the left and up, up, up on the right. So what they're going to tell you here is because the left side and the right side limit are approaching the same value of infinity, that means Right here. Okay, it approaches infinity as the limit. So now look carefully here, guys. Neither one-sided limit at x equals 4 exists. Therefore, we can conclude that the limit does not exist. However, because both sides agree, what does that say? Tend to infinity, we describe the behavior of f of x. Okay, so this is very confusing because you're like, wait. Does the limit exist or not? The limit does not exist because it's not approaching a value. However, think about n behavior, guys. You can describe the function's behavior as approaching infinity, but can you get to infinity? No, that's that argument that you always had with your siblings, right? Yeah, infinity plus 1, that's stupid. That doesn't mean anything. So, because it's not an approachable point, it's infinity. So the behavior approaches infinity, but the limit itself technically does not exist. This is a confusing concept for even in calculus. So when we get to the point of like, this is what your calculus questions will look like, it'll make more sense. Oh, see, there's, in a nutshell, that's a much nicer way of saying it. The symbols infinity and negative infinity do not represent real numbers. Right? Schooled all of your little 8-year-old selves. This is the fight in my house. Infinity gets thrown out a lot. All right, math teacher mom. Let's look at this one, guys. It's in your book. So just look on the board here, since you all returned your book. Look what happens on this function as you approach 0 from the left side. So on the left side, your function's, heading downwards. And on the right side, your function's heading upwards. So because your function is approaching two different ideas even on the left and right side, most definitely the limit does not exist, and we can't even describe the end behavior in a two-tailed notation. So I would only be able to describe end behavior on one side or the other, not both as a whole. Okay. So this is an example where definitely no limit, and I can't even describe the end behavior properly. Oh, you see that really stupid table that we all hate doing? Do you notice how the y values are approaching very, very, very different numbers? That's the algebraic way of you proving it's going to not work.
Is that like something we have to do?
I mean, in theory you could, but I'll be honest, guys, I don't, that's a good look, right? I don't really ever use my table, but that's because I have a very deep understanding of functions. So if you're like, well, I don't even know how to function, so how's that going to work? So I ironically have a deep understanding of functions, so I don't need to use my table. That's just always been the way my brain's worked. But there's nothing wrong with exploring the table. If you're not sure what this function does at that point and beyond that point, then yes, explore the table. And that is something you will do in calculus quite a bit. It's going to be like the very first few weeks of calculus, and you're going to be like, wow, this is tedious and annoying, but it's going to help you create a deeper understanding of the functions and how they behave. Well, that's fun. Okay, anytime trig shows up in your calc, and it shows up a lot, you got to remember trig functions are weird. So like, for instance, cosine of 1 over x, we have never had you graph that, but apparently it looks like that. That is called oscillation. And oscillation is where it bounces between two y values very, very quickly in some cases, but over and over and over again. So it's going to be pretty stinking hard to claim that it's approaching one value or another if it keeps oscillating between two values. So you're going to notice a lot of the trig functions are going to claim that the limit does not exist because of the oscillation. Oscillation is called a discontinuity in your textbooks. Okay. Let's look at these two trig functions though. So how about sine of 1 over x? As we approach 0. Can you guys tell what's going on here? Yeah, me neither. I mean, there's not even a scale there. So I think they're trying to claim that there's oscillation, so the limit does not exist. But it would have been helpful if they gave me a scale on the x-axis, so my bad. Well, it depends on how zoomed in they are. Because I don't really know right now. I don't know. We'll have to...
It kind of looks like there's a notch for 1 and... Like,
you think that's 1 and negative 1? Okay.
I feel like it is because there's like single notches going all the way down.
Maybe. I mean, we could graph it ourselves if you'd like to.
No.
Oh, no. That was a quick no from you. Well, can we investigate this one, though? I feel like that one's very clear cut. I don't see any oscillation whatsoever. So in this case, the limit is approaching 0.
How do you know if it's on a single scan?
Well, algebraically speaking, what would happen if you plug in a 0 right here, guys? What's the sign at 0? 0. And what's 0 squared times 0? 0. So there's no problem there, but there was an algebraic problem in this one, right? What would happen if you tried to plug in a 0 into this function? You'd have sine of undefined, and then you're like, wait a minute, sine of undefined, and then you're thinking trig, and then your brain shuts down, right? Yeah, so that's why you're seeing this oscillation of like between two different values, because if you think about trig being cyclical, yeah. So should we move on? Okay. I'm just going to keep watching. That's fine. So why limits at a point do not exist? Here's some reasons. And sometimes, and I think on your homework you're supposed to do this as well, you're supposed to claim why the limit does not exist. So it's one of three things. It's either that the function approaches a different value from the left side than from the right side. So that would be like your function is maybe doing this, and then maybe doing this. So there's some sort of a vertical asymptote where there's a break, a jump, a hop. Something is happening. It's going to approach two different values. We saw that step function earlier where it jumped, essentially. So it was like this. So that would be a good example of something where it approaches two different y values from the left side and right side, and that's why the limit doesn't exist. The other one is that the function increases or decreases without bound from the left or right. So that's fancy talk for... You've got that approaches infinity thing. So it goes up forever, it goes down forever. And then the third one is that weird oscillation. So oscillation shows up typically only in your trigonometric functions, like the couple we saw where they were oscillating between two values. So anytime you notice oscillation in your graph, you're going to have problems with saying that it's continuous and therefore it won't have a limit. Okay? Oh, this is so nice. Hofbauer, you're so sweet. She already graphed these for me. Now, she did graph them on an older calculator, so you might not notice this, but there seems to be like a connection on this graph. There's not actually a connection there. I don't think. I don't know. I don't think it matters. Talk to me about this function. Now, read carefully, guys. It says, and this is on your notes, it says, as x approaches 0 with a little plus sign. So that means... on the right side of 0, so I should be looking yonder, and it definitely approaches a specific y value. Can you tell from your seat there? 3, yeah. So this approaches 3, or you could just say equals 3 is fine. But if they asked me just a plain limit of 0, would I have been able to answer that? No, because on the left side it's approaching down here at -3, and on the right side it's approaching at +3, which are two different y values. So if it was the full limit, I would have to say it does not exist. Okay, number 2, and you might want to sketch what that graph looks like on your paper there. It's going to look like this. I'm not really sure about endpoints and stuff. Just draw that, and you'll understand what it looks like. All right, number 2. So again, we have a one-sided limit. If you're not sure what it looks like, you would graph it. Now, those of us who were thinking about tables, we could have done a table on this as well. Hey, thanks. You're welcome. So -2 is going to be a discontinuity for this graph because there's a vertical asymptote at -2. So they want to know, what about when you approach -2 from the left side? Well, I don't know. Where do you think it's going on the left side? Up, 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 and away. So even though the limit doesn't exist, you could say that the function is approaching infinity. Okay, so that's a confusing thing about limits in calc. The limit itself does not exist there, but the function is approaching infinity. I'm not going to be sneaky on your final exam and give you something weird like that. Okay?
So would you write that it approaches infinity and also that there's...
You would say that the behavior, the words your book uses is that the behavior tends to infinity. Which for us is end behavior, right? F of x approaches infinity. It's not the limit, though. A limit is indicating that you actually get to a number.
So how would you answer that? Would you just say that it's approaching infinity and there's no limit? Or
technically there's no limit.
So is that technically an answer?
If it said, is there a limit, your answer would be no.
But isn't that what number 2 is asking?
Kind of. I know. You don't like that answer. Just hang with me for a while. All right, so here, the graph, you might be a little confused what's going on, but I can tell algebraically that if you were to plug in a 2 right there, do y'all see you'd have an algebraic problem? There's a hole in this graph. You just can't see it on the calculator. So at -2, they don't indicate it because it's too small, but there is a hole there. But we're going to find out tomorrow there's an algebraic way to figure this out a lot quicker. What we would have had to do then is either look carefully at our graph and trace along it, or we could have plugged in numbers that were really, really close to 2. Now notice it's the full limit as x approaches 2. So I'm looking at both the left and the right side. The good news is they're approaching the same value. What value is it approaching? 7. Very good. So notice the difference in the notation there. I'll put equal 7. There's not an approaching arrow. That's the big difference. Okay. If it's an infinite one, just put an approaching. Be okay with that today. All right, so here, x equals 3, which clearly there's a problem because there's an asymptote here, and if I tried to plug in a 3, I'd have a discontinuity. So what we'd have to do now, because it is the full limit, so I have to look at both the left and the right side. You could either look at your table, or you could look at the graph, and y'all tell me what's going on there. So on the left side it's approaching negative infinity, on the right side it's approaching positive infinity. This limit does not exist. Now if they ask me a one-sided limit, I could tell them the end behavior of it, but not this way. If we separated them into one-sided limits, yes. But they didn't. So that is something you would do though. If the limit does not exist, you could indicate the end behavior as two one-sided limits. Yes. Confusing, I know. We're not going to like melt your mind on these questions, guys. When you guys go look at the review packet after learning today and tomorrow, you're going to be like, oh, these are pretty basic questions. I think I'll be okay. It's just the notation. All right, so here the limit as x approaches -2. -2 is clearly going to be a problem algebraically, so I'm not going to bother trying to plug it in. But if we look at the graph, oops. We have this vertical asymptote where both sides, left side and right side, are approaching up, 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 up. So even though the limit doesn't necessarily exist, the function is approaching infinity. All right, and then 6. 4, can't plug it in. It'd be a definite problem. Apparently there's a hole here at 4. A removable discontinuity that we can't see, but we know is there. So maybe on the table I would check out the left side and right side, or maybe on the graph I would trace. I'm going to give you another technique tomorrow on how to figure this one out. It involves algebra, so that makes everybody happy. But this time the limit is approaching 8 on both sides. Very good. Or I should say the limit equals 8 on both sides. All right, 7a has a little negative symbol up in the corner, so be careful there. They want me to look from the left side of -1, so I'm looking just here only. So again, the limit itself does not exist, but the behavior on the left side of that is approaching negative infinity. And then same function, but this time it's on the right side. So again, the limit is not going to exist at that point, but the behavior of the function is approaching positive infinity. So it's all about the notation. All right, let's talk about estimating limits. So, a few ways we can estimate limits. Graphically, numerically, and then tomorrow we'll talk about some more algebra tricks that we have in our tool belt that we can use. I'm a big fan of graphing it. I'm a big fan of using algebra. I am not a big fan of using the tables, but if I have to, I will. So let's talk about some functions that we already know all about. So 1 over x, a very basic rational function. I feel like I'm going to run out of time. Oh gosh. All right, so 1 over x is a rational function, and it looks like that over there. But if they say an infinite limit. So as x approaches infinity, they're asking you to look, this is like an end behavior question, right? So as x approaches infinity is indicating you to look at what side of your function. This is a very fancy way of saying to the right. So these functions, these rational functions, if you look along the right side, what y value does that tail start approaching? 0. Essentially, it doesn't get to 0, but we say it approaches 0, so the limit is going to be at 0 in that case. Now they did a table, and it was lovely. Notice what they did for the x's. They started plugging in gigantic numbers. But look what happens to your y values as you plug in a bigger and bigger number. They get smaller and smaller and smaller. So I don't tend to use my table. I tend to look at my graph, because this is where the idea of end behavior comes back, and you guys are very comfortable with end behavior, so I'd rather approach it that way. So here we have a different rational function, and then it says evaluate the limit as x goes to negative infinity, and that, we know from end behavior land, means the left end behavior. So look on the left side, guys. It's approaching this horizontal asymptote, which happens to be at y equals 2. So that means it's getting closer and closer and closer to 2. The limit equals 2. And they're saying it approaches 2. The function approaches 2. Let's take a look at some examples from your notes. On the back, please. Oh, there's our friend, the oscillation. Do you see it? Yeah, that's fun. Yeah. It oscillates between ever increasing and ever... Oh, man. That's fun. So on the left side, it's pretty cool, right? See how it approaches something? Neat. What about the right side? Yeah, it's very cool, but does it approach anything? No, it just gets bigger and bigger without bound. So this would be a case where there's a nonsense thing happening here. It's not approaching anything, but on the left side, you could say it's approaching 0. Okay. That's on your notes. That's on your notes. Is this on the back finally? Yeah, all right, cool. Man, Hoffbauer, you rock. She already got the pictures for us and everything. So if you weren't sure what this looked like, you would graph it, and we would see that it's a rational function. And they want to know what happens when you give me bigger and bigger x values. So this is fancy talk for right behavior. So on the right side, they went ahead and plugged in big, big, big x values. Look what's happening to your y values. It's approaching 2, so this equals 2. All right, so here, similar function, but a different one. And this time it wants, as x goes to negative infinity, so that's fancy talk for left. Oh, my pen isn't going to work. This will be fun. So on the left side, if you can see it on your graph, cool. You guys could also use that trace feature on your graph. Oh my goodness, what you doing? Sorry, my pen's possessed. Just a minute. On the left side, what value is it approaching? If you're not sure, go look at the table that she put up on the board. Seems to be approaching -3. Okay, there we go. And eventually your calculator, it says -3 simply because of like space of digits. But if you highlighted the -3, it'll start giving you the true number, which is like -2.9999. And eventually it'll give you scientific notation. And eventually it just says, you know what? It's 3. It's 3. We all agree it's 3? Uh-oh, it's -3, was it? Yeah, that's right. All right, so cosine, that's always makes me a little nervous when cosine and sine show up, because there's probably going to be oscillation, and sure enough, there is most definitely oscillation here, guys. So as I go to infinity, my function keeps oscillating up and down, up and down, up and down. So you're not approaching a singular value, and because of the oscillation, so it oscillates, write yourself a big note. So that means this limit does not exist. All right, this guy here, now notice, this time they want the right behavior. She plugs some stuff in my calculator, scientific notation pops up, but we're smart enough, we know what that means. This is teeny tiny numbers getting close to 0. Well, that one's fun. When I go to graph this guy, and I want to look at the left side, what's happening? It's going down, 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 down. So while it's not approaching a singular value, like an actual number, we can say that the end behavior is approaching negative infinity. that would be the two pieces of that end behavior line. Remember f of x approaches blank as x goes to blank? That's exactly what end behavior was, so that's nice that it came back. Isn't it? Don't you love when math things come back? All right, so here's an example of a sine function. There is a little bit of wiggling as you extend out, but look at what they're asking this time, guys, and this is what you and I were talking about earlier. This one, they're saying as x approaches 0 from either side, in this case, you can go ahead and tell me that it does come out to a value of 2. Okay? The other one I wasn't ready to commit on because I wasn't sure what was happening with the scale. The one a few questions back, where'd it go?
So what would happen with that scale?
Well, you'd be the one graphing it, so you'd know the scale.
Oh, it's just because you don't know what scale to put in.
Yeah, like this is not zoomed in enough. Like I can't even see what's happening here. And if I knew like this was, like if this was 1 and this was -1, this oscillation right here is actually a major problem for me and I can't really read what's going on. I'm wondering, I mean, if we had time right now, I'd go graph it myself. She's going to, okay. So I guess my point is I'm not ready to commit on this one. I would claim, right now I would probably claim oscillation. I'd have to investigate it further. When you guys go to calc, you're going to learn some more algebra tricks. We have a couple of applications that I would like to get to. I'll do them first thing tomorrow. But you guys do have some assignment problems I'd like you to look at. And there's a big note on my notes here. It says something about radian. Anytime you're graphing trig, you need to be in radian mode. Keep that in mind, okay? So if you're doing one of the trig questions, make sure you're in radian mode before you determine if there's any oscillation. Got it? Got it?
No.
Did she put your homework right on there, right? That's why we've been returning books and not feeling bad about it? Okay. Try a few of those, please. Please, please, please.
So it is oscillating between -1 and 1.
Oh, the height?
Yeah.
Okay.
And it does appear to be approaching 0.
Does it? Is it spreading out in the middle there?
What do you mean?
I'll look at it.